Without further ado, I'm going to introduce Zibra.
Yeah, thanks, Ian. I'll just start with an outline of what the project is. We contracted this company from Brisbane, Versailles, to do the acquisition of these seismic lines around Kalgoorlie. The preliminary interpretation was made by the company with part with our support. We actually spent a couple of days with the interpreter from the company, and we provide our regional common geological sense knowledge, let's say, to the interpretation. So it's a very basic and interpretation. We can use it as a starting point, let's say. And as Ian mentioned, the data were released to the public recently. And from our side now, we would like to start getting a bit more serious and work a bit more in detail on this data, structural investigation and geophysical investigation as well. And in total, so we acquired about several lines for about 300 kilometers from some 50 km north of Kalgoorlie down to the Kambalda area. And in contrast with other seismic lines that we acquired in the past, we focused in the upper crust, in the area that we can actually physically reach with the investigations. And yeah, I just want to mention, I will start mentioning what was my and survey previous experience. So the seismic lines that we acquired in the Murchison, in the northwestern part of the UN Mediterranean a few years ago. This was published as a JSWA report a few years ago, and then it has been feeding many ideas, many papers, because of course there have been very good data coming out from here. And what we did in this project, together with the seismic acquisition, then we ran a lot of structural work, a lot of field work in very well exposed areas, and so we were able to put together the signal that we have from the field, so structures at the outcrop scale down to the thin section scale and everything. Also, of course, acquiring information about metamorphic conditions, geometry, kinematics, and everything feeding into the bigger scale of the data provided by the seismic. And when we started, when I started working in this area, naively I was hoping to do the same, to have the same approach here, but unfortunately, what we know what I know now here, and what you guys probably knew already, that this area, despite being very generous in terms of mineral deposits, it's not very generous in terms of outcrop. There is poor exposure, much less than the average of the Egan, much less than the average of the UN Mediterranean for sure. There was widespread widening, and to add more frustration to the poor structural geologist, there is also the problem that the few outcrops that we have, they mostly expose underformed rocks. So the ice trend zones, most of them, they are systematically undercover. So it's very hard to obtain a statistically valid number of structural measurements. Of course, we have open pits. There are hundreds of open pits in the area, but again, they show mainly small-scale structures, and they're mostly late orogenic brittle structures, because that's where most of the deposits are located, and of course they are associated with a lot of weathering as well, so there are other problems. So how do we actually interpret, how do we obtain kinematics data and other metamorphic, for example, metamorphic data about the ice trend zones? That's one of the main challenges that we have for the future, and of course we'll try to obtain all the data we can from the available drill cores of the outcrops. But another way of working on this is to, of course, put the local data, the local geophysical data in the bigger picture that we know, or we're trying to build at the scale of the whole crater And this brings me to a lot of this presentation. So I will start briefly outlining what we know about, or some of the ideas that we have about the tectonic evolution at the scale of the craton. And then I will progressively zoom into the Kalgoorlie terrain and the Kalgoorlie area. And of course, providing I would say a quick overview on what is the seismic, what is the result of this seismic study. So we are trying to use the regional data to improve our understanding of the local geology here. And the angle I'm trying to give to this talk is that rather than trying to provide an exhaustive interpretation of the seismic line that we don't have, because we just spent a couple of days working with the company guys, and as I say, we'll be working on this in the future. But I want to just try to provide some food for thoughts about trying to think in terms of multi-scale. So most of you guys might be interested in structure on geology that occur at the kilometer scale or less, while the survey, as also Ian pointed out, often run surveys, geological, structural surveys, or geophysical surveys at the craton scale or WA scale. So one of the challenges is try to fit all the small scale data into the bigger picture, and we just try to think in terms of multi-scale in space and time. So going back quickly to what was our previous experience in terms of you and me survey. So this is a deep crustal survey. It goes down to the lithospheric mantle, and because the data that we obtain here in this upper crustal survey in Kalgoorlie fits well in the bigger picture, it's useful to have a look at what we see in the deep seismic surveys. So here we can identify a very sharp maw, of course marks the boundary between the crust and the mantle. Then we have a highly reflective mid to lower crust that usually highlights east dipping structural grain. And we have a heterogeneous upper crust where we can quite confidently link the geophysical data with the surface data, with the exposed geology. So it's mainly granite greenstone terrains. And from the studies we mainly conducted in the UME terrain, we know that this east dipping structural grain is connected to geometrically and genetically to the emplacement of many synorogenic plutons in a bulk transpressional environment. So many of these plutons were in place during transpression. Oh, that's the view that is driving mainly my work. And so we have three main crustal layers, an oblique fabric mainly deep into the east, and this is in striking contrast with what we see in the map view, which tends to offer kind of a quite symmetric anastomosed pattern of shear zones. And there are a few structures that are west dipping, but these are systematically confined in the upper crust, and most of the time when we see them, they post-date the east dipping fabric. And we'll see that it's probably the case also for the Kalgoorlie area. And this geometry actually is not just restricted to the UME terrain, but actually has been recognized in older seismic traverses that they ran in the past. We'll talk more about this one because it's obviously it's around this area here in Kalgoorlie, and this is the Leonora-Laverton line. So again, mostly an east dipping structural crustal scale grain. And again, even at the far eastern end of the craton, where the Archean rocks are mainly buried under the Proterozoic basin, again we recognize this dominantly east dipping fabric. So it's really a craton scale. And that's just a quick summary of what we see today. Well, the map is just mainly for the western part of the craton, but this applies well to the whole craton. So we have granite greenstone terrains, mainly representative of the upper crust, exposed, different terrains that probably got juxtaposed, or anyway, the boundaries of which correspond to major high strength zones. And we talked about this dominantly east dipping fabric, and this is a kind of a summary of all the available geophysical data. And remarkably, we have also the moor is inclined. It goes from about 30 Ks at the western end of the craton up here down to about 45 Ks at the eastern end of the craton. So the whole Egan is a kind of a wedge, huge wedge. And in terms of evolution of the Egan, well, it's been recognized that the early history of the Egan craton basically dates back to almost the time zero of our planet, of the Hadean. And the craton had an older nucleus, and then it grew through several episodes of juvenile input, so more material that was extracted from the mantle and accreted to the crust through several episodes of rifting, possibly. But this history is not preserved in the rocks that we can touch when we go in the field. It's more preserved. It's mostly or exclusively preserved in the zircon record, basically. And the oldest rocks, except for the small crustal slides that we have up in the narrower terrain, most of the rocks in the Egan, the oldest rocks are about 3.1 GA. And what we know from the data we collected from the exposed rocks, actually, that in the western part of the craton, in the UME terrain, we have a record of about at least 200 million years of greenstone development in a deep marine oceanic environment. So we have large amount of magma derived from the mantle and placed in the upper crust. That's from the UME terrain. It's a bit more cryptic, the record here in the Kalgoorlie terrain for these early stages. There are sequences that are equivalent in time to what we see in the west, but still not clear if they are remnants of these sequences or if they are just time equivalent sequences that developed in a separate environment. So I like to leave a question mark here in between, at least for this time that I defined as a pre-orogenic time, pre-orogenic stage, because we recognize a drastic change at about 2730, where we go from deep marine sedimentation to high energy continental to shallow marine sedimentation, subaerial volcanism, and the onset of syntectonic magmatism along these east dipping shear zones. So this sequence of events occur all together, and basically they are the signature of what we think is an important event of crustal thickening that marks the onset of what I defined as Egan orogeny, so at around 2730. And at this time, what we think was the eastern part of the UME terrain, which is marked here by this asterisk, got buried down to mantle depth, basically, under the Kalgoorlie terrain. So that's a possible interpretation. So these early stages of orogeny also basically marks the docking between the Kalgoorlie terrain and the UME terrain. And when we zoom out at the scale of the old craton, it's been suggested that this contractional event as the engine of that is basically the collision between the narrower terrain and the Murchison domain, possibly with a subduction zone here. There is also, this is based again on zircon, or the magmatic record basically in granitic rocks. But there is also good evidence from the greenstone in this area here. The material that is mostly still unpublished, but there is a lot of evidence here for subduction-related mafic magmatism. So it's possible that at around this time, at about 2730, we have a big event of collision between several terrains to form a craton that looks very similar to what we see today, basically. And after this stage of, let's say, assembly of the various terrains, We have the deposition of the Cambalda sequence that we know we started about 2720. So Cambalda sequence, Kalgoorlie sequence, sorry, it is confined, as we know, mostly here to in the Kalgoorlie terrain. So it postdates basically the docking, the suture between these two terrains. And so what we see today is basically an unconformable, mildly deformed, unconformable contact between the two generations of greenstone. So that's a possible interpretation. And after this, we have a record of, again, shortening, important crustal shortening with other syntectonic plutons emplaced around 2680 to 265. And we work a lot on this Candimara Pluton in the west, but it is also relevant for this talk tonight is what happened here in the Kalgoorlie terrain with the Ballard shear zone, which is basically coeval with this one. And we'll talk more about this, of course, because I believe this Ballard shear zone, the deformation events occurring during this stage are the one that they shape the bulk of the features that we see here in the Kalgoorlie terrain. And after this, we know that east-west shortening continued, and the formation seems to have switched to one of the few west-dipping structures that was associated with the granite emplacement. And during this stage, which is one of the youngest orogenic stages that we see, one of the youngest important ones, we have the final exhumation of this Warunga greenstone belt that contains remnants of those high-pressure rocks that developed early in the orogeny. And so this Warunga greenstone belt, actually, it's a kind of a window into a journey from the upper crustal development here at the bottom of the ocean and in a pre-orogenic stage through burial at mantle depth or lower crustal depth at the onset of the orogeny, and then final exhumation towards the end of the orogeny. That's the cycle of the greenstone and at the eastern margin of the UME seems to have recorded. And as I said before, we progressively zoom in, so we arrive at the scale of the Kalgoorlie terrain. And I just want to start doing this little exercise of comparing the geology of the Agnew area. And this has been studied, as you say here, these are the published work for the last 40 years, from Platt in 1978 till basically today. And I tried to do a little exercise, and I tried to compare, these are mostly structural work, I tried to compare the number of deformation events that people identify through time, and we obtain this kind of graph. So we start from 2 deformation events in 78, we arrive to a peak of 10 deformation events in 2012, then we go back to 2 and 3. And of course, this is a challenging, it's a challenging situation for structural geology, or for geologists in general, because I mean, if we cannot find a straightforward agreement at the scale of a single greenstone belt, it's going to be very challenging in trying to match the deformation or the structural evolution of this belt with the, for example, the greenstone in Cambalda. You know, it's a very difficult thing to do. And so, what's a possible source of this discrepancy? And of course, they can be variable accuracy during field work. People can use different techniques, have different background. So good. Mostly, I believe it's a matter of scale. Again, the importance of scale. So we look at the same rocks, but we see different things because maybe we think a different scale. And we know briefly that the formation can be punctuated, can be continuous, progressive. Often it's just a matter of resolution, and we tend to find many more fabrics in areas that have higher degree of lithological complexity and possibly lower metamorphic grade, so typically in the greenstone. It's very common that you recognize several fabrics at a small scale in a greenstone belt, and then they all seems to merge in a single fabric at a regional scale, typically in a shared zone centered in granites. So these are all things that we have to try and keep in mind. And another point about scale is that, of course, here we can have large-scale shear zone, normal shear zones, like in the case of the Himalaya, which are developed in an environment that is characterized by bulk crustal shortening. Again, it's something that we have to keep in mind, particularly in areas where we are now in the Egan, where there is little outcrop and most of the information can be, it's probably not accessible, so you can really lose what's the really important signal is it can just be preserved just locally. So you really need to be mindful where you go, or you simply need to go everywhere. And so one possible way to overcome these issues, the scale issues, is to work on granite tectonics. So this is a bit my background. And of course, structural geologists in the Egan and basically most Archean terrain, I believe, they mainly focus their work on greenstones. This is mainly, well, because they are more economically more important, also because they're usually better exposed. As I say, you can recognize several fabrics, so you can do a lot of nice, fancy work. But of course, there are small-scale things. So when you work at plutons or shear zones that are hundreds of kilometers in size, as the case of the Egan, of course, you are working at a scale that is more appropriate to try to get a feeling of what the real crustal scale processes are, the first order events that shaped a craton. And another important point is that one thing that has not been recognized is most of these shear zones that we see centered on granitic plutons, they actually developed while the pluton was being emplaced. So this is an important point that has been traditionally overlooked, mostly because people didn't look at thin section scale, or it's just a matter of how our knowledge evolved also. But simply, I mean, this is not a lecture about granite tectonics, but simply I want to just outline what the importance of this point is, the importance of being molten. So if we shear a rock in a melt-free environment, say by homogeneous simple shear, we can obtain something like this, assuming that this is pretty homogeneous. But if we introduce a very low viscosity layer, which is the case of melt, for example, in between a greenstone package, we obtain something like this. This is a kind of a drastic example, but it's quite close to reality, I think. Of course, we obtain a lot of strain localization and strain partitioning as well, and this is mainly due to the very low viscosity that the magma has while it's still partially molten. And has been shown, this situation has been shown to have an important influence even on the post-magmatic tectonic activity. So these are probably the events, in my view, that are the events that actually shape these Archean terrains. And then there are, after this, there are minor events that basically rework these structures. That's my view, at least. And zooming into, actually, finally into the Kalgoorlie terrain, I've been working on this Ballard shear zone, which is a kind of a big structure. It's at least 200 kilometers along strike, going from about the latitude of Menzies up to Agnew, and then basically, then it's up here, it's truncated by younger structures, so it was probably bigger in the first place. We have two nice seismic lines that intersect these structures, so we know this is the line at the Kalgoorlie latitude. We know that, as I said before, most of the fabric is dipping, while in the north, this structure again is truncated by this late orogenic Wollonga shear zone. And we know that also this Ballard shear zone was active about in the 2680 to 65 MA time span. This is basically constrained by the age of the deformed granite and the age of the truncating and deformed granites. And when you go in the field, it's very clear that the bulk of the fabric in these rocks was acquired during flow of partially molten rocks. You have beautiful semagmatic features in the thin orogenic granites. These are the riverina gneiss, so slices of the pre-greenstone basement of the greenstone, basically, which are invariably migmatitic. And you see a lot of these structures. So these nice boudinage of this fibulite injected by leucogranite melt. So this is occurring during Pluton emplacement. The greenstone slivers that you find within this shear zone, they are invariably migmatitic. So this is a pretty strong signal, and this is confirmed also by microstructural work. Invariably, you see a very high temperature deformation fabrics acquired again in a temperature compatible to the solidus of granitic rocks, so around 700 degrees. Nice microstructural evidence of melt present deformation. And you do see solid state fabric, but this is typically confined to the margin of this large scale shear zone. So it's basically the Pluton that crystallizes and cools down to the ambient temperature, the temperature of the upper crustal greenstone, and is still deforming during cooling. And you have beautiful myelonites again, but this is just the very late part of the story. The bulk of the shearing occurs during low viscosity flow of the melt bearing rocks. So when you put together all the structural data, you have clear evidence of strain partitioning. So the granites are mainly moving strike slip, and the greenstone on the shoulders of the shear zone, they're mainly doing flattening. So these are the main ingredients of transpression. So you have strike slip with a component of horizontal shortening. And this is nicely goes from the map scale down to the thin section scales. When you go in the greenstone, you see weak layers that they mainly localize simple shear deformation, so they go strike slip. And the adjacent mafic layers is a garnet and fibulite, dominantly go with pure shear. So you have irrotational garnet grow here and nice snowball garnet here. These layers, they are basically 5 centimeters apart, strain partitioning. And there is also crustal extrusion. This is the scale of the whole shear zone. So these systems are bounded by a reverse shear zone at the base and a normal shear zone at the top. At least some of these shear zones, they show these features, and the barrel shear zone is one of them. And so these are the definition of crustal extrusion. So the high grade, the hot core of this shear zone, it basically gets extruded towards the surface during granite emplacement. And the greenstone at the margin of the barrel shear zone, in these rocks, we locally have synkinematic assemblages with garnet, staurolite, and biotite in the felsic schist, garnet and fibulites in the mafic layers. So we don't have metamorphic data yet, quantitative metamorphic data yet, but from these assemblages we can say that they reflect peak conditions at least in the order of 3-4 kilobars. So these greenstones were buried at about 10 kilometers depth, basically shortly after their deposition, and this is, to me, is another signal of this crustal thickening induced by transpression. So basically in the Kalgoorlie terrain, and this is a sketch that tries to summarize the two main deformation events that shaped the Kalgoorlie terrain, which is probably part of the same progressive event of east-west shortening. So we have the Bala shear zone, and then the formation switches into the Warunga shear zone, and we have a sedimentary response basically during the development of this shear zone. And what about extensional event? Because people talk about extension. Of course, there are structures that have been described in some local literatures that have been observed, but they are usually small-scale structures. So the question is, they could be part of the overall contractional structures, so local extensional events, or local extensional structure accommodating big contractional ones, or reactivations. Or of course, often they've been postulated, well, there is a sedimentary basin, so therefore we need extension. Well, no, it's a very weak argument. We know that we can develop sedimentary basins in shortening. So in my view, the unambiguous identification of extensional structures, at least in the Kalgoorlie terrain, is quite difficult because of the younger strong overprint that we developing shortening. They might be there. In my experience, I haven't seen any convincing evidence, and they might be difficult to identify. What we know also from the stratigraphic record is that, and there is a lot of work from these people, some 10, 20 years ago, they described the main stratigraphic sedimentological features in the Karawang, from the Black Flag basically to the Karawang formation. So all the package of all the various unconformable basins that overlay the mafic, ultramafic rocks of the Kalgoorlie group, and they all seems to have been deposited in linear zones of subsidence. The paleocurrents seems to indicate that the material, the sediments were fed from the north. So from what we know here is the Ballard Shear Zone, and there is regional control on development of these basins. So it's as opposed to local control, and all seems to fit well in a strike, in what they defined at that time as a strike slip environment. And these guys, of course, at that time there was no knowledge about the Ballard Shear Zone, so we have independent evidence of a kind of a strike slip transplational environment. And a similar picture was offered here a few years later. So again, we have a strong signal of shortening. So we have a kind of good convergence between structural data, metamorphic data, and stratigraphic data, and they all talk about shortening, probably in a transplational environment, in my view. And finally, we zoom in again, the Kalgoorlie area. This is a nice map from the survey in the early 90s. What we see here, what are the main features here? We know that at that time, the Zuleika Shear Zone, which is mainly this yellow line here, was identified as a major feature in the area, and I agree on that. There is no, I guess it's confirmed also by the new seismic data, as we'll see in a minute. And another important point is that just a basic analysis of what we see in the map. We have a series of south plunging antiforms here. They are the most prominent features north of Kalgoorlie, and the situation is reversed in the south. So the Kalgoorlie area is actually a kind of a structural basin. So we have the uppermost structural levels are preserved in this area, and we are basically along the same Ballard Shear Zone that is basically up here, just at higher structural level. What we see in the area, and this actually, maybe I should have put this map earlier, but anyway, this newer version of that map that I showed before, and they actually show the arrays of the lines that were acquired during this recent survey. So we say that we have a network of 7 lines covering about 300 kilometers. They are mostly orthogonal or at a high angle from the major structures. So they are in the ideal orientation to show the true geometry of the structures. And what was the main structural style that we have to expect? So we are, as we said, we are in the very upper crust, and of course we have the youngest deposit here is the Karawang Formation that was deposited in a very shallow marine continental environment probably, and has never been buried significantly. So basically, we are still in the very upper crust, and we are probably in the upper structural level of the Ballard Shear Zone, which is the equivalent of what I've been studying up here, is probably sitting here under these rocks. And so, of course, we have to expect zones of broad contraction in the strong layers, mafic, ultramafic layers. We'll try to develop this synform and antiform that we can follow in the map. So the blue are the antiform, and there is a series of synforms. But you see the limbs of these structures have been truncated in a way that is similar to what I imagine is what has been pictured here. So once the limbs of this fall, they become steep, it's easier in a bulk transplational environment. It's easier to localize the formation along the steep limbs, and I think it's probably a good representation of what happens here at this scale. So this is the seismic line that was acquired back in 91, I guess, and then was interpreted. The interpretation was actually published in several papers, even years later. And this is relevant, of course, because it's just running a few kilometers north of us. We are around here, and it's running very close to our line number 1 and also line number 2. So hopefully we can match the structure that we see, and it's also important, of course, because this is a deep seismic survey, so it's offering again a crustal scale image of the crust, of course, of the upper mantle and the crust, and so the data we acquired now, they will have to fit in the upper portion of these images. And again, what we see is that we have dominantly an east dipping fabric and west dipping structure confined in the upper crust. And this is what these yellow lines are outlining. And so finally, we get into the actual data that we recently produced. So we are at very detailed scale. And what are the main features that we can recognize here and we can actually match with the surface geology, so we can identify what we think is the Kalgoorlie group that produces these strong, prominent reflectors, and we have a good confidence with this because, of course, they come up at near the surface, so we can match them with the exposed geology. And then we have in between we have these transparent layers that possibly, at least some of them, they probably correlate with the black flag and the other sedimentary sequence on top of the mafic ultramafic sequences. And then we have some broad transparent zones that can possibly be interpreted as granitic plutons and granitic gneisses that probably have this kind of anisotropic signal here, but less prominent than what we expect to have for mafic ultramafic rocks. And then finally we have these patches that are a bit enigmatic, but they can probably represent the zone of alterations because they seem to be kind of truncating all the measured structures, and they're kind of transparent patches. So, as I said, what we see here in this new seismic line seems to match quite well what we can expect from the observation of at the map scale. So we have kind of an open, broad folds, kind of a locally disharmonic folds associated with the main, with the more competent rocks of the Kambalda, the Kalgoorlie sequence, and then we have probably sharp shear zones that may be localized. They can exploit the contact between the felsic and the mafic rocks, and of course it becomes more difficult to identify them because we don't know if we are just looking at the sedimentary contact or a stratigraphic contact or a tectonic one or a combination of the two. So that's one of the possible challenges. And of course we have an overall listric architecture even at this scale. So when we are in the field we are mostly looking at very steep structures, but we can see that they get pretty shallow relatively early when we go down. And again, that's kind of a representative example. We can see here we can trace a line between two prominent packages of reflectors. They seem to be discordant. But again, what is this? It's a kind of a primary feature. Is an unconformity between, so it's a feature that developed during the position of the greenstones, or it's a tectonic contact, or a combination of the two. And it's very hard to answer for the moment, at least. And of course, we always have to keep in mind that we're looking at a 2D representation of a possibly complex 3D structure. So these are some of the possible challenges that we have to face when we try to interpret these lines. But anyway, just want to point out with this that these lines, this data, they offer a very high resolution. So, and this is not, you can zoom in even further. So There's plenty of room for you guys to play and produce. There's plenty of room for you guys to produce your own interpretation. And again, here this is actually one of the images that the company put in the report that you can download from our website. There is a quite good match from the central portion between the central portion of the historical EGF line from 91 and the line number 1 that we acquired close to that. And again, we see that the Zuleika seems to be one of the most prominent features, one of these east-dipping features. Again, in the upper crust, truncated by one of the west-dipping structures that correlates with what in the field we call Bardock shear zone, and which seems to be younger and displace the Zuleika shear zone. And this is one of the attempts that the company tried with providing a kind of a synthetic view of all the data. Obviously, it's a very low resolution image, but I like it because it kind of provides an overview of all the data, and I try to color code what the structure we recognize across the line. So it seems that we can recognize the Zuleika shear zone in basically all the 7 lines, and then there is a sequence of west-dipping structures confined to the area basically east of the Zuleika. It seems to correspond to this network of splays basically that seems to truncate or be associated, possibly be active during the same time as the Zuleika shear zone. And as Ian mentioned before, kind of in parallel to the seismic acquisition, there is a project that has been running, led by Mike Densis at UWA, acquiring empty and passive seismic data. And we actually literally got this data from him a couple of days ago, so there is not much I can say about this. The first, of course, this is still work in progress. There will be much more coming out soon, but the first, at first glance, we can say that there is a very good correlation between the data that has been acquired recently through MT and passive seismic. Good correlation between this data and the data acquired in the old EGF seismic line, and this applies both for the MT. Applies to both to the MT and the passive seismic data, and in particular the IDA fault seems to be associated with a major change in crustal geophysical properties. Again, the Bardock shear zone as a kind of a this is the MU fault here that marks the boundary between the Kalgoorlie terrain and the adjacent Canal terrain. Seems to impressively coincide with another marked change in seismic property. And so this is still work in progress, and as I said, we'll know more soon about this. So just to conclude this talk, we started big at the scale of the craton, and we said that basically my view is that the craton, the Egan craton, and possibly many other Archean terrains worldwide, they were shaped by during major orogenic cycles through events of transpressional pulses associated with the emplacement of tectonic granites. And of course, this has a profound influence of how we interpret the large-scale seismic data. And when we zoom in the Kalgoorlie area, we saw that the idea that we are running is that the Kalgoorlie at the scale of the Kalgoorlie terrain, the bulk of the geometry seems to be related to two major events of crustal thickening associated with bulk east-west shortening, possibly during a single progressive event during the orogeny. And finally, the seismic data that we just released seems to at first glance seems to match pretty well with the previous seismic data and with what we know from the geological picture. Finally, again, we want to stress that we're working for you guys as well, so the data are out there. Have your go, and in the meantime, we'll keep working on this. And I'll leave you with this.